Okay, so when we have a function, our function is increasing if as x gets bigger, y values get big. So if you think about your slope, you have a positive slope value. Versus if our function is decreasing, in other words, as x gets big, y gets small, we call that a decreasing function, which would have a negative slope. So we're going to take a look at this investigation, and we're going to go ahead and, for part 1 here, differentiate f, in other words, find the derivative. So when we take the derivative of this, we get f of x equals what? Minus 12x. Okay, good. So that's the derivative. So now what you guys are going to do is from here, I want you to find the value for f prime of x at each of these values. So now go ahead and substitute each of those x values into your derivative function and get your outputs. What do you notice about the sign of the gradient? Because that's what we just calculated here. We found the gradients at all of those individual x values. So this is the slope at -2. This is the slope at -1. So if you look at your graph, at -2, so right about here, there's my slope. At -1, that looks like that point, there's my slope. So what do you notice about the slope when your x values are negative? They're positive. Good. Therefore, is f of x increasing or decreasing when x is less than 0? Increasing. Good, because it has a positive slope. Now for number 3, what do you notice about the sign of the slope when x is between 0 and 4? They're negative. Therefore, the function is decreasing. So I'm doing 2 things. I'm looking at the derivative, and I'm looking at the slopes, and then I'm going back to the function, and I'm talking about whether it's increasing or decreasing. And then f, when x is greater than 4, it's positive, which means the function is increasing. Good. So therefore, what do the signs of the gradient of f of x tell you about whether the function is increasing or decreasing? So if the gradient is positive, the function is increasing. And if the gradient is negative, the function is decreasing. And it's a little bit logical with that too. I mean, if you think about it, if my slope is positive, it's getting bigger. My slope is negative, it's getting smaller. Okay, flip the page. Notation here. If the derivative is greater than 0, so in other words, if my derivative is positive for all x in the element of, a backwards bracket, remember, means excludes it. We usually use a parenthesis, so that'd be parenthesis a, b parenthesis. And then f is increasing on that same interval from a to b. Again, it does not include those endpoints, because a lot of times those endpoints, it's going to switch between increasing and decreasing. So we cannot equal it. It can't be both increasing and decreasing. I want you to think about that. Don't say anything, but I want you to think about what happens when a function is going from increasing to decreasing or decreasing to increasing, and that's where that interval is going to fall. Same thing here is if my derivative is less than 0, if it's negative and x goes from a to b, then my function is decreasing from the interval from a to b, again, excluding those endpoints. If it's the end of the function, we may be able to include it. We're going to see some examples which should hopefully clarify the prompt I wanted you to think about, and then also what happens when we have that endpoint. So in order to do that, we are going to find the intervals where each function is increasing and decreasing. We are completely doing this without our calculator. We are not graphing this function. I'm not going to look at it. Like here, I could look at, oh, I can see it's increasing. Oh, I can see it's decreasing. Oh, I can see it's increasing. If I don't have that picture to look at, I strictly need to be able to use my function. So if we want to look at increasing and decreasing, what do you think I have to do to these functions? Take the derivative. So go ahead and take the derivative. We're just going to do a right now. Okay, so now I need to figure out where is my function increasing or decreasing. What happens when it switches from increasing to decreasing? So therefore, what's happening between increasing and decreasing? What do we know about the derivative? It's 0. It is a horizontal line when it goes from increasing to decreasing. So I need to figure out where does that happen. So I set my derivative equal to 0 there. So please go ahead and solve for x. What you're finding is these points of inflection, which is talking about where is increasing and decreasing changing. So go ahead and solve that equation. So now that we know where my x values are 0 in terms of my slope, what I can now look at is I'm going to do what's called a sign diagram. A sign diagram helps us keep track of negativity. A sign diagram is where our values change from positive to negative, from negative to positive. Okay, so I know at -1 it's 0, and at +1 it's 0. So it's going to possibly change from positive to negative or negative to positive within here. It doesn't always change. And as we keep learning more and more about how graphs work, we'll figure out some cases where it does not change. Okay. But for right now, we're going to be really looking at mainly where these are changing. So in order to figure this out, again, this is for my derivative right now. I'm doing the sine function for my derivative. If I put a value into my equation that's on each side of this, it'll tell me whether my slope is positive or negative. So if I want to look at what my slope is at -2, I put -2 into my equation, and do I get a positive value or a negative value? Positive. So all of my slopes are positive when I have values less than -1. Now I can pick a number in between these two, in between -1 and 1, such as 0 is a perfect one to substitute in. So into my derivative function, when we put 0 in, I don't care what the number is. Is it positive or negative? Negative. And then I put in a number that's bigger than 1. And folks, it's fine to pick giant numbers like 100. That's not a giant number, but a big number. It will work out perfectly fine for you. So if I put a big number in, am I going to get a positive out or a negative out? Positive, because this whole thing is positive, and when I'm subtracting a 3 out, so that's positive. So based on the sign diagram, I now know where my function is increasing and decreasing. I know the slopes, which is what tells me whether it's increasing or decreasing. So this function, the original function, is increasing from -infinity to, what value does it stop increasing at initially? -1. Parenthesis, because it does not equal those endpoints. Union, because it starts increasing again. Don't forget your union symbol. And then we start with our low value, which is 1, up to infinity. And then decreasing. Where is it decreasing? -1 to 1. What we can do now is, based on some of this information that we just did, we can graph this. And the reason we can graph it is we know when we have the 0 value, that we know where we have a horizontal asymptote. So at -1, I can figure out what my point is. So I can calculate f of -1. F of -1, I need the coordinate point in my original function, not the slope at -1, because what's the slope at -1? 0. And then I'm also going to calculate f of 1. It's going to give me the coordinate point at 1. So take a moment, put -1 in for your x and put 1 in for x. Okay, so I substituted in these values into x to figure out what my coordinate points were. And I graphed the point -1, 6. And I graphed the point 1, 2. So those values have a slope of 0. And then I know where it's increasing and decreasing. It's increasing from -infinity to -1. So at -1 here, this is where it stops increasing. So increasing means it has a positive slope. So it goes this way somehow or another. And then at this point, it has that turn of some sort. And then from -1 to 1, it has a negative slope. It's decreasing, so it turns around down to that value. And then from 1 to infinity, it's increasing, so it turns around there and starts curving up again. So if you remember back to Algebra 2, when we graphed cubics, we were able to calculate our x-intercepts, and then we drew a curve. And I said, you will not be able to find what these high points and low points are until we get to calculus. You are now in calculus. You can find these high-ish points and lowish points. Questions? Now I'm going to have you guys do B without a lot of my support. So for B, I want you to figure out your increasing and decreasing intervals, and then I want you to sketch a graph of it as well. So your derivative is 2x. So when you plug in a value smaller than 0, so when you solve it, you get 0. When you plug in a value smaller than 0, like -1, it's negative, so your slope is negative. When you plug in a value that's larger than 0, it's positive, therefore it's increasing from 0 to infinity, and negative infinity to 0, it's decreasing. Now, you all know this graph because it is a parabola that is shifted 1 unit down. However, without thinking about that fact, calculate f of 0. When you substitute 0 in, you get -1. So it's the point 0, 1. And then it's increasing from 0 to infinity. It's decreasing from negative infinity to 0. Now, you don't necessarily have that perfect parabola shape, but you do have that parabola in there. We're now going to get into these like highs and lows along the way because we can have multiples of these. So we have what's called an absolute min, also called a global min. An absolute min or a global min is the value of y is the lowest in the entire domain. So the global min is where you have the lowest possible y value. Whereas a local min is going to be a turning point where the gradient function has that sign change. And I'll talk about that in a second. But local min, you're thinking like smallest within that region. Absolute max is the value of y is the highest in the entire domain. So it's the highest possible y value. And then local max is going to be, again, a turning point where there is a sign change in the gradient function. So the absolute min, the absolute lowest point in this graph is A. Absolute max, the highest point is D. And then local min, local max. Which one's the local min? C. And which one's the local max? B. So the local min, C, occurs when it goes from decreasing to increasing. C goes from decreasing to increasing. So slope is negative, 0, slope is positive. A local max is at B because it is increasing, 0, decreasing. Increasing, 0, decreasing. Another way you can think about it, for a local min, it's has a negative slope to the left and a positive slope to the right. I just talked about increasing and decreasing. So we can use what's called the first derivative test to determine if we have local mins and local maxes. The first derivative test helps us find local mins and local maxes. So if our derivative equals 0, we're going to check our turning points. Okay, so we're going to be testing our turning points because sometimes they're actually not turning points, they're just critical points, and we're going to talk about that later on. Sorry, inflection points, not critical points, inflection points. So if my derivative is greater than 0 and x is less than c, and the derivative is less than 0 when x is greater than c, there is a local maximum. So my derivative is positive as we're coming from the left, and then my derivative is negative as we're going to the right. That has a local maximum at that c value. Whereas if my derivative is negative when it's coming from the left, and then my derivative is positive as we keep going after c to the right, there is a local minimum. So you're going to see me draw these pictures a lot when we're starting to try to graph an entire function. Because what we're going to give you is we're just going to give you sine functions, and then we're going to say, here, graph this. Or I'm going to give you the graph of the derivative, and you're going to have to be able to graph the original. And so we're going to do a lot of these pictures to help us see where are my local maxes, where are my local mins. But before we do that, here's one more of these problems that I'm going to have you now do from start to finish. So what we're going to be looking at is we're going to be finding those turning points. We're going to be looking at where does my function increase or decrease, just like we finished up before. And then we're going to talk about local mins and absolute mins and maxes. Okay, so if we're going to start this, what is the first thing you're going to do? Take the derivative. And now that we have the derivative, what are you going to do with the derivative? Set it equal to 0. And you're going to factor it. Good. Greatest common factor. 3x. Good. So where are my turning points? At x equals 0 and 2. Good. Do your sign diagram. When we evaluate the positivity based on the sign diagram, sometimes it's easier to use the factored form. So for instance, if I'm going to put a value in like -1, if I put it into the factored form, it's usually a little easier to see. So if I put -1 in here, 3 times x, so 3 times -1, is that positive or negative? And then if I put -1 in here, -1 minus 2, is that positive or negative? And a negative times a negative is a? Okay, sometimes it might be easier just to put it into the original derivative, but a lot of times the factored form is a little bit easier to work with. So then if I put in 1, this is positive, this is negative, so positive times a negative is a negative. And then I put a value in like 3, this is positive, and a positive times a positive is a positive. Okay, so I now know my increasing and decreasing. But before I can do that, let's find our turning points. Okay, so with that in mind, I had that value at 0. What's its y value? 4. And I had the value of 2. What's its y value? 0. Again, we're just putting into the original function to get what those points are. So let's state what we know about those points. 0, 4. At 0, it's going from a positive slope to a negative slope. Is that a local min or a local max? Max. Because it's going from a positive slope to a negative slope. And then for 2, it has a negative slope and then a positive slope. Therefore, at 2, 0, it's a local min. We won't know absolute until we look at the endpoints of our graph. Okay, so that's the first part. So that's part A. Part B wants our intervals for increasing and decreasing. Now, it has endpoints here. So this does not go to negative infinity. The lowest value you can have is -2. And are we including -2? Yes. Okay, so from -2 to 0, it is increasing. So square bracket with -2, 0 parenthesis, union, parenthesis, 2 to 3, and square bracket. Good. So decreasing goes from 0 to 2. Exclusive. Correct. Good. Then for C, state if the points found in A are local or global extrema. So what I have to do is I have to figure out what happens at the ends of my graph. What happens at the ends of my graph. And honestly, if you're not 100% sure what the shape is, you can always pick a number that's past it to see, does it keep getting bigger, or does it keep getting smaller if you just aren't seeing it. Here I have a value I can look at. So I have to look at f of -2, and I have to look at f of 3. And I need to see if these values are bigger or smaller than my local min and local max, because that local min and local max may change. It might not actually be a local, it might be an absolute or a global. Okay, so calculate f of -2 and -3, please. Okay, so when you substituted in -2, what'd you get out? -16, that's what I got as well. And when you substitute in 3, what do you get out? 4. Okay, so I have these coordinate points, -2, -16, and 3, 4. So based on that information, absolute min, absolute max. Do I have an absolute min value? Yeah. Which one is? So -2, -16 is an absolute min. Also called a global min. Do I have an absolute max? Yes. So here's the interesting piece. These both have a height at 4. So at 3, 4, we will call it both a local and absolute max. Yes, because they both have the same y value and absolute max. Okay, the last problem then. This is a different looking graph. So we're going to use a derivative to show that the graph has no turning points. And then we're going to state the intervals where it's increasing and decreasing. Even though it has no turning points, it does increase and decrease. And then we're going to sketch the graph based off of that information. So to begin with, if we're going to use the derivative, I've got to do the derivative of this. What are you guys thinking when you see this? Quotient rule. Don't use the quotient rule. Nope. You could, or even easier, there's a single thing in the denominator. Divide the numerator by the denominator. Yeah, because there's a single thing there. So it's x over x minus 5 over x. Divided the whole numerator by the denominator. Does not work when there is a subtraction or addition in that denominator. But it does really make this problem much easier to work with. Oh, they do, but then that 5 is still divided by x. So now do your derivative. So now, if we're using that derivative, we're going to set it equal to 0 to figure this out. So 5 divided by what value gives you 0? Nothing. I cannot divide number by anything and get 0 out. Therefore, there is no turning point. However, what is present in this graph? An asymptote. There is a vertical asymptote in this graph. At x equals 0, good. Asymptotes also can control increasing and decreasing, not just zeros. So we'll always do two things. Typically, first, you're going to look for that vertical asymptote. And second, you're going to look for your zeros, because they can have both things as well. So we are going to do that sign diagram. And the way we represent that is at 0, we put 3 dots here. Okay, so now with our sign diagram, just like we did before, into my derivative function, here it is. Into my derivative function, I'm going to put a value in above 0 and below 0 to see what I know about my slopes. So when I put a value in like 1, is it positive or negative? And if I put a number in like -1, is it positive or negative? So it's not changing negativity. It could. Okay. But, so now I know this function the entire time is increasing. There is no decreasing. So this function is increasing from, nope, yep, unioned with 0 to infinity. Good. So right now I know where my vertical asymptote is. I know the slopes are increasing the whole time. I now need to look at my horizontal asymptote. This is something that you all should remember. At y equals 1. Degrees are the same in the top and bottom, therefore it's the ratio of your coefficient, 1x over 1x, which is 1. So when we sketch this graph, now the whole time my graph is increasing. Is that increasing the whole time? Is that increasing?
No.
Is that increasing?
No.
Is that increasing?
Yeah.
So it's the ones where they're increasing. So therefore, it's those two. Okay, so we just went through a ton of stuff. So we went through using your derivatives to find increasing and decreasing. But in order to do that, we need to look at where it's 0, because that's where it's going to possibly change. And if it's not where it equals 0, then we're going to be looking at it based on where its vertical asymptote is. That's the other place where things can change, whether increasing to decreasing, decreasing to increasing, or neither of those. Again, completely depends on the situation. We're going to next move into second derivatives, which are going to tell us more about our slopes as well. But that's for another day.